Our moderator is Jim Free. I went through Jim's bio, and there's no way I can tell you everything that he's done and everything he's worked in. He's been essentially everywhere, including the deputy director for Glenn and director for Glenn. Now he's back home as the chief operating officer and senior consultant at Leadoff DX. So Jim, you want to take it away?
All right. Well, good afternoon. It is really great to be here today. Thank you for this opportunity. I want to thank AAS and Jim Way and the team for allowing me to be here. It is a great honor to be part of anything associated with Senator Glenn. Having had the privilege of working at and being the center director for his namesake, I had the opportunity to meet him numerous times. And he had such a great spirit about him, I think is the best way to put it, spirit for exploration and just really commitment to the agency. I think the last time I met with him, he asked me about a technology that he had gotten funded during his last term in the Senate, and he wanted to know the status of that technology. What was funny was I didn't know, and here the senator knew more than I did. And also it was nice to hear Marla highlight Mrs. Glenn. What a great spirit and what a great couple they made together, and had the pleasure of meeting her. And actually, I was her date at his 90th birthday party. I was her person that walked her around. So it was a tremendous opportunity. So let's talk about the panel we have today on opening nuclear thermal propulsion pathways. And I think the things to highlight there are, the options we have for NTP today, where we're talking about advanced materials, new fuels, new missions that this technology can enable. And to have that discussion today, we have included a couple folks who I think would be great to hear from. First is Mr. John Abrams. He's the Vice President for Advanced Projects at Analytical Mechanics Associates. John has his BS in Mechanical Engineering from South Dakota School of Mines and Technology, and his master's in aeronautics and astronautics from Stanford. So welcome, John, and thank him here today. And then our second panelist is Ryan Whitley. So Ryan is on loan from NASA to the Executive Office of the President, and he's the Director of Civil Space Policy at the National Space Council. Ryan's worked in a number of exploration jobs in his time at NASA, and has his BS in Aerospace Engineering from Purdue and his Master's in Aerospace Engineering from the University of Texas. So John and Ryan, welcome. We're really looking forward to hearing what you have to say. And I would invite John to take the floor if we could pull his charts up, please.
Someone can give me the thumbs up when they're up.
Yep, John, you're on.
All right, well, thanks everybody. Thank you, Jim. Thanks for the panel and AAS for putting this on. I've been supporting nuclear thermal propulsion now for just a little over 4 years. I don't consider myself an expert actually, but I have a lot of people that I work with that truly are experts and have been working with NTP for decades. And I'm gleaning a lot, and I'd like to take in a somewhat holistic view, because it's not just about the technology, but it's really how you implement that technology and sell it and understand what its true capabilities are for enabling space exploration. So I recognize I have quite a few slides here, so I'm going to try to go fast to enable that we can have plenty of time for questions and discussions after this. So moving on to slide 2. Just want to start off with some fundamentals. This might be remedial for some, but others it may not be. But what enables nuclear thermal propulsion? And it's, hence the name, it's really about the nuclear energy source. Nuclear energy has been used for terrestrial power systems for over 70 years. And it's really energy density of the fission system, fissioning uranium-235, that enables nuclear technologies in space, but namely NTP. Just to give you an idea, 1 kilogram of uranium that is fission is the equivalent of 2.7 million kilograms of coal being combusted. So that's the equivalent of 1,000 days of a megawatt of power. To give you a little further idea, an NTP system that takes a human mission back and forth to Mars is only fissioning on the order of tens of grams of uranium, less than a sugar cube's worth of uranium that is actually fissioned as part of that process. So that energy density is really what enables everything when it comes to nuclear systems. So because of that, the NTP engine is actually pretty simple. It's a heat exchanger, really, with some traditional turbo machinery wrapped around it. And in fact, the simplicity of it and the performance of it is the stuff that's wrapped around the reactor is actually lower temperatures and lower pressures that would be used in normal chemical propulsion systems. I.e., you can leverage that heritage and you actually have more margins when you're doing such. What really powers that is we're using hydrogen, just hydrogen as the propellant. It's the lowest molecular weight propellant out there. And since you don't have to combust it and lobbing on that really heavy oxygen atoms, it's very lightweight, and that's really what enables the high ISP. And we're talking on the order of 900 plus seconds of ISP, twice as good as any chemical system. So moving on to slide 3, NTP is not new. It's been around for quite a while. Fission systems in space are actually not new either. US has flown a fission reactor back in 1965. And the Russians, former USSR, has flown dozens of them. NTP in particular has not flown, but it does have lots of ground heritage, starting back in the 50s with CERMENT development. But the big program mostly during the 60s is the Rover-Nerva program, technically 2 programs, combination of NASA and DOE. But they built 20 different engines and tested them under 23 different test campaigns that were going on for minutes of burn duration. It was real development, real work back then. The fundamental difference between them and then and now is highly enriched uranium was used. Now the focus is on low enriched. Other projects were going on between United States and USSR throughout then, but it's been a lot of studies up and down since then. And although I was not a part of those, what I have heard from those that were is that what we're doing right now is probably the greatest amount of momentum since that has occurred since the Rover-Nerva days. So I'd also like to point out with respect to heritage of NTP is a lot of people know Kennedy's speech at Rice University back in 1962. Everybody knows the first part about getting a man on the moon. Really successful at the third part of using space for communications. What a lot of people forget about is Kennedy really brought up using nuclear systems to get people beyond the moon to Mars or deeper interplanetary exploration. So it's been thought about for quite a while. Moving on to slide 4. So what's the value of NTP? It's really a combination of high thrust and high specific impulse, the gas mileage. Thrust helps you get out of the gravity wells. The high specific impulse is really what enables you to make smaller systems. Smaller systems is less stuff to throw up in space with your launch vehicle. It reduces costs, and it's a pivotal element to work within the budget constraints of what we're talking about to foremost get humans to Mars. So that enables fast conjunction class missions and also opposition class missions for getting humans to Mars, as illustrated in the top right of that slide. It's robust in that it has engine out capability, has ability to leverage the systems into like bimodal systems, produce electricity. You can do aborts, given that high thrust, high speed combination, much further into the mission that you could otherwise do with a chemical propulsion system. Going on to slide 5. Just a second. So what do we need? We know the value of it, but where do we take it? Especially since we're working with low enriched uranium in kind of a different environment than the Rover-Nerva days. And the first thing is it's about high temperature materials. Jim said this, it's a materials development project. not just making sure these things don't melt, but how do they operate? How do you define and certify the conditions at such high temperatures? We're talking on the order of like 2,800 Kelvin. How do they operate neutronically? How is their thermal performance? How is their mechanical performance at those elevated temperatures? And how do they interact with each other? Namely, how does it operate with hot hydrogen and the corrosive aspects of hot hydrogen? Going on to slide 6, another development need is, and this is almost an opportunity versus a need, that again, the systems are fairly simple in theory, but what it is screaming for using today's high performance computing and multidisciplinary optimization techniques is to really squeeze out the capability of a nuclear system. There's lots of parameters and dials that can be moved and adjusted throughout here with respect to the composition, geometry, how you control it, how you wrap thermodynamic systems around it to really prove out higher and higher performance in a system. Going to slide 7, another development need is, yeah, you can design these things on paper and you can do small scale development, but ultimately you're going to have to get to prototypic scales in order to certify it, especially for human rated systems. We don't have those facilities laying around. They're going to have to be developed. And so it's a combination of factors that need to be pulled together in order to get to those prototypic sort of conditions that are frankly outside of what normal aerospace verification processes are, because you're thrown in that nuclear aspect into it. So it's things like transient flux, the total dose, it's adding hydrogen in there, and it's all doing it at very high temperatures. We have these capabilities now at small subscale and when you separate the variables, but as you want to pull these variables together and go to higher and higher or larger and larger scales, we're going to have to move forward with new facilities. So the trick here is how do we do that intelligently where the facilities are not the critical path of development? And there's a lot of work being done on trying to figure this out. Moving to slide 8. So a big aspect of facilities or verification in general is the regulatory aspect. These are inherently safe and secure systems, but you need to do that through processes to keep both the public and the environment safe. And so things have changed through time since the Rover Nerva days. The Nuclear Regulatory Committee didn't even exist back then. But still processes are in place, but it's the nuances of those processes that we move forward in this new realm of development that will truly get worked out the first time we move through it. And so I'm just showing some stuff up here on a slide on the number of regulatory bodies and steps that are involved, which are systematic and can be done. It just needs to be conscious that that is a big part of the overall project. So moving on to slide 9. So how do we do this? There's some development needs that need to be done, and there are solutions. And taken at the highest level is an emphasis on it, and it's a national prominence. And that's occurring right now, not only at NASA, but at DOE and at DOD, namely some of the projects that are going on. I've been supporting, and multiple others have been supporting project under the Space Technology Mission Directorate, under the Game Changing Development Office for nuclear thermal propulsion. That did a lot of work on feasibility, fuels development, mission architectures, kind of the top down, what we need from level 0 sort of requirements. The project has since moved into a different program under STMD, Technology Development Demonstration Mission program. And it's now moving into, while hardware was done before, its hardware is full on what needs to be done right now to bolster these technologies. I think a lot of people know that this is not just NASA. DARPA's big into this right now. There's BAA out on the street. I think it's due in August, where DARPA is looking to do an in-space flight demonstration of an NTP rocket for cislunar operations. So I can just say that this national recognition is good. and that it is one of the primary drivers of which is moving forward. So what's the other part of the solution? I think in the earlier panel, Steve Jerzyk was talking about it's the people. And I think it's the people for creating anything in NASA, at Glenn, across anything aerospace, because it's somewhat niche skill sets, and those need to be harnessed and bolstered. I find NTP very attractive due to its combination of really interesting stuff. The combination of aerospace and nuclear, I think, would attract lots of people and is attracting lots of people if we push it forward. And so this sustained knowledge base, I think, is very important for keeping the project moving forward, because it's going to take a while. Any technology like this is going to take years to develop. Maintaining that base of skill set is very important. And not just for NTP, but there is synergy with other space nuclear systems. Jim Bridenstine mentioned earlier about the emphasis of surface power on the moon, and that's the same fundamental skill sets that are involved in developing systems of mechanical engineering, nuclear engineering, and the thermodynamics, along with evolutionary pathways to nuclear electric propulsion, which has really high promise of ultra high ISP performance in exploring the solar system. So I'm really excited. Hopefully this is a little bit of information to seed some questions and discussions. Thanks, Jim.
Thank you, John. That's great. Yeah, actually, I never knew that was the second part of the president's speech. So I definitely learned something today. I appreciate that. And the vision of only a few grams for that total mission time is fascinating too. And it'd be interesting to talk about reusability of those stages when we get to the discussion part. So I'll plant that seed with you. So let me turn it over to Ryan, and I look forward to hearing what you have to say, Ryan. Thanks, John.
Thanks, Jim. Like Jim said, my name is Ryan Whitley, and I am currently the Director of Civil Space Policy at the National Space Council. And so what that means is we work on policy issues across the space sector. Now, my portfolio focuses on civil space, but in the case of nuclear, it actually is a whole government thing that John was alluding to. It's bigger than just civil. And I'm going to broaden out a little bit in my discussion here. I'm going to talk a little bit more about nuclear in general for space. So not just propulsion, but power as well. And so, going forward, it is this administration's policy to invest and to prioritize space nuclear power propulsion systems for space as appropriate and as needed in a very safe, secure, and sustainable way. So nuclear power is not new to space. As John alluded to, we've done some demos in the past, but we even today use a form of nuclear called radioisotope generators, RTGs, that we use to go deep into space, because solar energy is something that we lose as we go further from the sun, and so it's very important to have a power system that can keep those systems going. Now, those are very small systems and very modest means. So when we want to do bigger missions, whether they be robotic or human, we will need more power. And so that's where fission reactors come into play, and where we get into this discussion about transportation. So they can power all kinds of systems, spacecraft, rovers, surface systems. They operate in environments that some places you can't get power, such as the long days on the moon, where we can have 14 days of darkness, or on those craters where there is no sunlight at all. So if you need some other types of systems that will help you. And like John mentioned, NTP is going to be a very efficient means to travel around the solar system. Now, it may not be what we need for moon missions, but it will be what we will need for future Mars missions going forward. So the Space Council is working on policies to bring together the national goals, not just in exploration, but also in defense, to look at the kinds of things we can do from a whole government lens. And so we are working on policies associated with these goals. Some of these goals we are looking at in the near term include developing of a production line of fuel. We have discovered that something called HALEU, which stands for high assay, low enriched uranium, is a fuel form that can be applied to many different systems, both terrestrial and space, both power and propulsion. So we want to establish the capability at the government level that will eventually, hopefully, become commercialized in the different fuel forms. And then our immediate need is not propulsion for exploration, but is power. And that's what we're going to need on the lunar surface. So you heard Brian Stein mention that earlier. So we are prioritizing a fission power system for the moon. We need our missions to really pull the technologies. The technologies on their own are interesting, but they really need to be driven by the mission need. And then eventually, we will develop the nuclear thermal propulsion technologies that we will need for Mars and beyond. Now, at the same time, we won't give up on our radioisotope power systems. That's still going to be important going forward. So we're going to have power systems and nuclear forms as appropriate, as needed for the various missions. And also, John mentioned safety. That is an important part of what we're doing here. You know, there's some myths out there about nuclear energy and how dangerous it is. And while radiation is obviously something that's important to monitor, these are not the same as your huge power plants. And now even those power plants, I think, get a bad rap. But you know, our small modular reactors have very small amounts of uranium. You know, and they're not enriched to a high level when they're low enriched uranium. And so they really don't present the same kind of safety problems. So there is some policies about launch regs that have recently been passed that allow us to more easily cut through the red tape and get systems into orbit in a more efficient manner. So in general, we are at the Space Council are looking to look at the whole government, to look across the agencies. So we, Don mentioned DOE, DOD, NASA. We want all those government agencies to be working together collaboratively to help each other further this. If we all work in our silos and don't work together, it's going to be that much harder to make these things happen. So we're looking to see those agencies work together, and we're seeing fruits of that labor already going forward. So we look forward to seeing that development. So I think that's all I have for now. So happy to take questions or discussion as we move forward. Thank you.
Okay, thanks, Ryan. I definitely want to hear more about the common fuel when some of the questions I'm sure we'll get from the audience, and a couple that I thought of too. And it's you really, I was going to put that seal over my shoulder today, but I don't want to show off. No, thanks. Great insights. And I think policy, the technology drives so much here, but the policy side is really, John showed all the agencies, right? Pulling all those together, and especially with where nuclear certification rises to the president's level, folks driving that policy like you and having a technical understanding is very helpful as well. So thanks for your insights. Okay, I know it sounds like we have 2 or 3 questions from the audience. I'm gonna hit a couple of mine as the prerogative of being the chair of the panel, and I'll see where they go in terms of who wants to take it. I guess I'm going to get the elephant in the room taken care of first of all, and you both hinted at it, and maybe even stated a little more explicitly, but NTP versus NEP. I'm not asking you to say which is better or more viable, but how do they exist together if they can at all? And I'll let either one of you answer it, but I'll ask both of you to answer it.
I'll go first if that sounds good, Ryan. So how they can exist together is they have a lot of overlapping capabilities, and there's different models for technology development. There's push models and there's pull models, right? We're somewhere in between right now, where there's a lot of from NASA's perspective, a lot of architectural constructs that could use both NTP or NEP. And then there's a lot of development underneath that is doing a push. So it's somewhere in between. But where they meet is what I was talking about a little bit in that last slide I had, is it's in the people, in that a lot of the capabilities overlap, and they overlap now. A lot of people that are thinking about NTP, let's say people that are thinking about NEP. And a lot of it is at Glenn right now. There's expertise throughout Glenn that is looking at both and have looked at both. And so they can coexist in the same environment. Obviously, where they're going to struggle is limited resources when it comes to budgets. But I think time and technology development will flesh that out through time.
Yeah, and I agree completely with what John just said about commonalities, and that is where, at the policy level, we're really pushing, and that's why reactor design is really important to us. We think even a fission service reactor can play forward to both. Now, the main difference, the way I understand it, I'm not a nuclear engineer, so that caveat aside, the way I understand it, NTP requires higher temperature reactor, right? So it's a matter of how fast do we move to that kind of form? And my understanding is you can use a similar form factor, similar types of low enriched uraniums. It's just different coatings of that fuel, or different ways to put that together. So we can learn a lot on either one of these paths. So I won't, I'll maybe beg off the question a little bit and won't compare and contrast them directly, because I know NASA's doing studies there. I don't want to preempt that work that's going on. NTP has value for NASA, but the other selling point for NTP is it has a value for DoD that was mentioned earlier. Is needed for those applications that require quick maneuver capability, which NEP does not have that capability. So that's one thing that weighs in heavily, and if we're going to really see commonality as much as possible, that would be a nice thing to see NTP be applicable to both. But like we've talked about, there's pluses and minuses to both, and so it's not easy necessarily to make a clean decision there. But I think we just need to get the ball rolling. That's been a number problem. A lot of things we talk about. Well, we need this now. We need this finished product, but we have to build it into steps. And so I think from a policy standpoint, we're pushing some of these early steps that will move the ball down the road so that we can accomplish these bigger objectives.
Okay, thanks. I think I understand you walk a fine line there, Ryan. I guess from my perspective, I'd be asking, and I know STMD is doing the study, so I'm sure it'll get looked at. But from an internal NASA perspective, I think the centers have worked well across the nuclear world. I'll just say nuclear. I won't add a T or an E after it. It's can we make the best architecture decision, and what's the nearest term? Like you said, right? Surface power is probably the nearest term, but you also can't let NTP slip, right? Because you're always going to be 7 years away from flying NTP. I think Ellen Stofan used to say that quite a bit. We're always 10 years from going to Mars, and that bar just keeps sliding out, right? And the longer you let the development lag, the further you're away. Okay. I want to pull on a point that John had in his charts about testing. And I think it applies to policy because you have all those agencies in there, and you're going to need some help if you choose one path. But I'd like each of you to talk about testing what's better on the ground or just launch and test it in orbit.
I can go first. So, yeah, there are a couple schools of thought on how we initially verify the system. One is obviously a more traditional approach of developing the facilities where you can do all of it on the ground. Another school of thought, due to potential regulations and other benefits, that you can maybe do it faster if you just go directly to demonstration. We actually led a study of a big group of industry participants on how you would do a flight demonstration mission for NASA requirements. And then DARPA's obviously pursuing their in-flight demonstration. There is merits to both, and there's challenges to both. I would say on the ground, it's more schedule and the regulatory aspects, which we and others have done lots of trades and studies on. There are avenues to do that, whether that's at a NASA site or at a DOE site, and we've even looked at commercial sites to build those facilities of auto testing. On going directly to a flight demo, the kind of flip side that you need to think about and where the investment needs to be applied is how do we think a priori that we're firing this up for the first time in space, that we thought through all the hooks and gave ourselves enough margin and put in enough equipment, test equipment basically, or sensors and whatnot while it's in space to pull down the data that you need once it fires up. So one, make sure it fires up, operates like the way you think it's going to. But two, do you have the right infrastructure to pull down the information so it adds a lot of value? So there's different trades-off there with kind of schedule versus more the technical aspects. There's value to both, and I'll let the higher level decision makers comment on which way it's going forward.
Well, I'd say the details, choices between ground and orbit is not necessarily a policy decision, although it's a budget one that we have to weigh in. And I think, again, going back to what I said before, mission pull is a big part of that. And so, the mission need for NTP is for Mars, and, X number of years. We're not looking in this a need in this decade, but like Jim said, you don't get started, you're not going to get there. So we're hoping, or looking toward DoD to be leaders in this area. Now, I know there's debate about scale and applicability to deep space missions, but I think really with the Draco program that DARPA is doing, I think there's really an opportunity to do a real demo there. That'd be valuable to everyone. So if NASA can engage on that, that'd be very valuable. DOE is going to be leading in the testing category, right? Because they're the ones that NASA is going to be partnering with to have the certification to use these nuclear materials. So on the power side, we really want to see that happen right away. Ground testing leading to you can call what we put on the moon a demo, and I think that demo, flight demo, even though it's not propulsion, is going to be very valuable for nuclear materials in general. We haven't really tested the regulation on launch yet in any meaningful way, so that'll be a big thing to go through when that happens. So we do need it in space applications, but it's about the mission pull. I think that's really going to drive that, because we know that budgets are always tight. Trying to play the priorities there is going to be difficult. So we're going to probably need to do mostly on ground activities in the near term, leading to some flight demos. But the ones I see are going to be led either by DARPA for propulsion or the DoD, and then on the NASA side, we'll probably be doing power first.
Okay, great. Thank you both. Jim, why don't we make sure we get the questions from the audience answered? Could you share a couple with us?
Sure, Jim, thanks. So yeah, we've got a few questions actually coming in. One of them, I'm going to combine two of them. So one is, do you all feel that there's sufficient coordination and a clear role definition between the agencies that need to support this development? For example, are nuclear reactor design tools being shared between agencies, or are they being developed in more of a stovepipe fashion? And the other question was somewhat related. Are the NASA and DARPA projects in NTP sufficiently different for them to be independent, or are we missing an opportunity for them to collaborate and cooperate? I know that's a lot, but I'll let it go there.
Want to go first again, John?
Yeah, well, Ryan, why don't you go?
Okay.
Why don't you go? Yeah, I think you have that overarching view.
Yeah, no, we care very deeply about collaboration. So we are writing policies as we speak to try to promote better collaboration. Now, it doesn't mean it hasn't existed and it hasn't been happening. I cannot speak directly to how DARPA is interacting with NASA. Actually, maybe John knows more about that. I don't know the direct interplays, but they are the missions are different, and so the systems and requirements are different. So that makes it hard to sometimes get those requirements all the same. Now, on the power side, I know we are trying to on the fuel side, for example, make that a commonality. And so while the reactors in space are going to be different from the ones, for example, on the Earth, which we departments are also looking at making small modular reactors for terrestrial applications, there are going to be differences. So it's where we don't want to force commonality when it doesn't make sense, when you're really going to hurt progress and efficiency of the systems. But where it does make sense, we're looking to see that happen more, and we want to encourage that more. So we don't want dead-end applications or dead-end developments that don't help one another. So where that is lacking, we're going to push for that more going forward. Some of the specifics I don't have, on the NTP side, I can't answer that. Maybe John can. But on the power side, I know we're really looking to make that a priority going forward.
Yeah, so I would say I do believe federal agencies are coordinating appropriately right now. As Ryan said, I just want to echo that the missions are different. DARPA is not trying to send 140 to hundreds of metric tons of stuff to Mars and back, right? So it's a question of scale. And so the designs are going to be different, but at the fundamental fuel level, there's going to be lots and lots of commonality. And DOD and NASA are right now executing plans to work together, and DOE, to execute plans to develop fuels together. So there's collaboration there. And I would say specifically from the NASA mission, DOE and NASA have been collaborating hand in hand. DOE is in the NASA org charts, overseas stuff. And so I think there's lots of collaboration at that level.
And I guess I would just add, I think it's never the wrong time to continue to talk about roles and responsibilities and who's going to do what, and be very clear about it. My experience, and I was part of the machine adding lack of clarity, I guess, to it, of not really defining this is where my interface is. Could you draw the interface and say, here's the reactor DOE, this is what the interface looks like to my to my engine and my tankage. I mean, you could draw it that clearly. I think that should always be something that's looked at. The NASA DOE relationship has improved a great deal over the past number of years, in my opinion, from reworking MOUs, MOAs under Robert Lightfoot's tenure through the way it executes today on the RPS program. So I think taking those lessons learned and adding the clarity is something you should definitely do. And the other thing I'd add is kudos to NASA Space Technology Mission Directorate with their Space Technology Industry Government University Roundtable, where they bring together people. I was at one, I think it was last year, where the subject of nuclear came up, and maybe it was earlier than last year because Fred Kennedy was still at DARPA, but DARPA was there, the universities were there, DOE was there, and they were talking about nuclear and who was doing what and where the commonalities were. So I think it's better than it has been in the past, but certainly as people and administrations change over decades, you ought to make sure you continue to revisit that. What's next, Jim?
All right, I got another question for you. So AMA has led NASA's industry study on NTP this year. Could you guys talk about some of the non-proprietary innovations that you're seeing out of that?
I'll try. So drawing the line there on what's proprietary and not, and the reason is I'm just very sensitive to just competitions that are going on right now. Namely, DARPA's doing that. And even though we just said they're different missions, there's still a lot of commonality. So let me try to paint with a broad brush. Industry, and I'll just say specifically who helped us out, or who were the industry partners, and I'm going to talk really on the reactor side, was X-Energy, General Atomics, Ultra Safe Nuclear Corporation, and BWXT. And each one of these companies bring forward design approaches and strengths that are packed full of innovation, whether it's at the fuel level or it might be on a more global optimization level of the reactor design. And so a broad range of concepts have been looked at from the fuel standpoint, the reactor standpoint, on the geometry, on the heat transfer configurations, if you will, even on the controls aspect. I can't get into details, honestly, but what I can say with confidence, there is a lot of innovation coming out, and it's just not a rehash of what was done back in the 1960s. This is using techniques that are enabled by today's engineering to really push the capabilities of what an NT. Sorry, I can't go into details, but I am very impressed with all the innovation that's coming through from industry.
Okay, thanks, John.
Okay. Should I go ahead with another one, Jim?
Sure, go ahead, Jim.
Okay. This one has to do with fission. So one of our attendees observed that the electron bombardment thruster was developed at NASA Lewis back in the early 60s, and its descendant wouldn't fly as the primary propulsion system until Deep Space One in '98. And NASA Lewis did a lot of work on this. NTP is yet to fly. The US has only done one nuclear fission power system for space, and that was in '65. How do we break that trend? How do we fly, when we know the future exploration in a timely manner? And what are you looking at with respect to safety in respect to fission power?
I'll take a quick stab at some of that. So yes, what is different this time around? Well, I think part of it is we have to convince or explain how nuclear power is not the same kind of danger that some people think it is. I mean, we're not talking about, we can't have a Fukushima type accident on these systems. It's just impossible to do. And so we have to be cognizant of what the safety issues are and attack and work on those. So for a nuclear reactor, power or propulsion system, there are three phases that you have to really deal with, and that is launch, ground testing first, launch, and then operations. And so we have all kinds of regulations in place for ground testing, and it's very well established. We have brand new regulations from last August about launch. And if we focus our development on this low enriched uranium, it's not the same kind of proliferation problem, so we don't even have to have that issue as much. So the safety issues are very manageable, very things that we can prove out and take care of, and we don't have to worry about the dangers of the radiation even, because it can be packaged and you can't, and for fission reactors, they're not turned on all the time. You can turn them on as needed. So it is, I think, an education project in some ways. If the general public has a reaction to it, or a congressman or other leaders, there's an education aspect to that. But really, to get forward, it does require funding. And so we have to have focused funding on the programs that we need and have measured steps, so a roadmap of sorts. So these are all things that folks have thought about many times, and so there's always risk to them not happening. But we're really working, at least from the Space Council perspective, to bring all those things to bear, to think about the steps, to think about the safety issues, remove those burdens as much as we can, and encourage collaboration, and hopefully we will achieve those objectives. I mean, it's never a slam dunk, but when you have a good mission pull, it helps with that as well. So I'll leave that from the policy perspective. There's probably other thoughts the other guys have.
I'll just make a couple comments. I think Ryan's spot on in that everything he said. I'll steal an anecdote. When it comes to safety, I'll steal an anecdote that Dr. Mike Houts at NASA Marshall says a lot, and I think it's good. That, hypothetically, if we're in the trenches of developing a nuclear thermal propulsion system, 5-10 years from now, whenever it is, who's at greatest risk of it receiving the most radiation dose from that project? It's not the technicians working in and around the reactor. It's the project manager who's flying back and forth between meetings, talking about safety, because he or she gets the greatest radiation dose from just being in an airplane versus the folks that are developing nuclear systems. I think it's very well known and regulated, and safety precautions are spot on. We just need to do it, and I think the risk will be incredibly low. And we need to explain that to the public and all stakeholders. Just to touch on what Ryan was talking about when it comes to funding, it's just a recognition that, at least from all perspectives, space is not necessarily easy, and it takes resources, and you got to recognize the payoff for investing those resources. And the starts and stops are what really inhibits you. So you just kind of need to do it. And I'm really impressed all the way from a congressional level, recognizing that, yeah, it does take real resources in order to pull this technology.
I guess I would just add, I mean, the example that the participant gave about something in the 60s and not flying until Deep Space One, you know, it's a risk thing, that the risk always sounds worth it at the beginning until you get to PDR when you're trying to get to TRL-6, and then the program manager says, I can't take that risk. I'm going back to the thing I know works. I think this is a little bit different because it really enables what it decreases in trip time for humans and cargo capability. And then you both said it, right? The budget and the sustainability of the budget, right? You can't get $100 million 1 year and then go into a CR and drop down to 20 million and then go back up to 80 million in July when you have to spend it by September 30th. And that budget sustainability, there's a performance aspect to it. I think one thing that always gets lost is that systems engineering function on the front end when it's TRL 2, 3, or 4. How is engineering involved there, where it's it is more R&D, so that it can transition better on the back end to the higher TRL. It's not as big of a leap. And then on the safety side, you know, I mean, I'll say RPS, right? There's still people that have that concern about putting nuclear material in orbit today that are probably going to be around for the launch coming up of Perseverance, that just in principle don't approve of it. I think finding the simple ways to explain nuclear safety to folks is the best way to do it, and start that now. It's not a campaign you start 2 or 3 years before launch. It's people have to start talking about it today. Okay, Jim, do you have any more?
Yeah, I've got 2, and why don't we make them just for fun, short answer questions? How about that? So the first one is, should NASA wait to finish developing NTP before attempting Mars human exploration?
Nobody's mute button went off after that.
I can go. Jim, let's see if I got it right. Should NTP, I'm sorry, could you just repeat the question? Let me
Yeah, absolutely. Should NASA wait to finish developing NTP before even attempting human exploration of Mars?
So it depends on what you mean by attempts, but obviously you need the propulsion before you can launch. But I don't think you should wait, absolutely not wait, on the development of all the other systems that need to be a part of a human mission to Mars and wait to see if the NTP propulsion technology comes forward, because we do not have the luxury to put things in that sort of serial order and wait that long. There's lots of things that need to be done in parallel. And the propulsion aspect of it, which is very important, not going to get there otherwise, but it's just one element of it. So,
yeah, the question assumes that NTP is the long lead item, right? I don't know what the long lead item is. There's so many things we need for a mission to Mars, which is why we're doing the moon first, because the moon provides that proving ground to do a lot of the surface things that we were going to do on Mars, that we have to do on Mars. You know, a Mars round trip, even with NTP, is still months, years potentially, depending on how you do it. So you're going to need technologies that can last a long time. So we're going to have to do a lot of work on multiple areas to do the first mission to Mars. And we want to invest also in public-private partnerships. And so NASA be dictating all these solutions is a big question. So we want to do the technology development to allow companies to take advantage of that in the future. I don't know if all the companies who want to do Mars are going to say they have to use NTP, but you know, we think it's has huge benefits, so we're going to invest in it, or we're going to push that investment, right? So, what comes first? I mean, we have to think all those things together. And like John said, it has to be a lot of parallel activity or it's not going to happen at all. So I guess I'm not convinced that NTP is the long pole necessarily for doing the Mars mission. There's a lot of things we have to do to make that work.
Yeah, so shorter answer is for me is no. It should not wait for NTP to be done. You have to, EDL is a huge challenge. You got to get a bunch of stuff down to the surface. We still haven't done anything greater than we're going to do here in 6 months once Perseverance hits there, and you need a lot for the crew on the surface. You need a lot for them in orbit. You need communications. There's a lot you can do in parallel while NTP is going on that you can push out there that can wait for the crew. All right, Jim, you said you have one more.
I do, and it comes from Al Tadros, who we just heard from a little while ago, one of our sponsors there at Maxar. Can you talk about the importance of refueling NTP systems and the vision and work that the U.S. government has done in that regard? So refueling architectures is what he's looking at.
I mean, I can talk a little bit about it. This is not, me as a Space Council person talking about refueling, although we're looking in general for ways to make space exploration cheaper. And so reusing systems is a high priority, right? We know that, just to follow an example, SpaceX has developed reusable rockets, right? And a lot of other companies are looking at the same thing. We are gonna need reusable systems across the board to do these missions. So yes, I think refueling of an NTP system makes a lot of sense. Now, hydrogen as a fuel is cryogenic, it's difficult to handle. We have to develop the proper technologies in space to be able to handle cryofuels and cryofuel transfer. We have work being done at NASA to address those issues. So another parallel activity, right? We just talked about parallel activities. This is something we need to work on as well. So yes, I think we want to focus on refueling, not just NTP, but all the systems we use in space, because propellant is the biggest mass drivers of any space mission. Humans.
Yeah, I would just add, I think it's an evolutionary aspect to NTP, and the priorities are probably different between DoD and NASA. From a NASA's perspective, let's just say going to Mars perspective, it would be an evolutionary pathway that would further bolster the value proposition of NTP. And one thing to point out, when we say fuel sometimes on NTP, we mean the nuclear fuel, the uranium that's inside, and we call the hydrogen the propellant. It's really hard to say repropellant though, so I understand what it means by fuel. It could be really enabling, and there are technologies that are being developed now. I mean, that is autonomous rendezvous and docking. You got to have a system to come up to the other system in order to refuel it. So that's a big one that is cross-cutting across multiple technologies that should be developed because it's necessary for just example, for getting to Mars. A lot of the stages have to be autonomously put together, staged in orbit. And so refueling, autonomous rendezvous and docking is a major aspect of that refueling aspect. Cryogenic fluid management is the other tall pole that needs to be done with respect to refueling. And that needs to be done regardless. It needs to be done regardless for a mission to Mars, for DoD missions, and even if for whatever reason it decides to go to strictly chemical propulsion systems, CFM is still a critical technology.
I definitely agree with that, John. I think you're going to need to refuel. You're going to need to do propellant transfer, I'll say it that way, and long-term storage of cryogens on the surface of the moon, for instance, to refuel. If you're taking hydrogen and oxygen up there, you're going to need to do something. If you have LOX methane, you're going to need to know how to do that. So I think you have to do that at some point regardless, and it could be applied to repropellanting an NTP stage. So okay, well, thanks, Jim, for getting us the questions. I do want to thank again Jim and Alan and Carol and the whole AAS team for for setting this up. Certainly Ryan and John for putting the time and thoughtfulness behind things, and the questions too. Having been on these for a number of years, it always makes it better when the audience is involved, right? You're all here today because you've chosen to be here, and I appreciate those folks that ask questions to really get their thoughts out there. So I guess just in closing, I started by talking about Senator Glenn. He really was an inspiration, and he got us down this path of exploration by putting himself on top of that rocket. So it's great to talk about putting folks on top of a rocket that's going to go further and farther than we've gone before. So